let's get started. Okay, let's see my camera. Okay, so thanks everyone for coming. This is our the Ask Seminar series, and I'm John, the seminar coordinator. I will be moderating this seminar with Kathy, who is our communication manager. And also join us is our Associate Director, Ralph Ferrero, and Ralph will be introducing the speaker. Just so you know, then this seminar is being recorded and we will publish the recording on our YouTube channel. So for anyone who miss out, you can check out our YouTube channel. And the Q&A session will be after the presentation, and we encourage you to bring up any questions you may have. You can do so by unmuting yourself and asking a verbal question, which is preferred. You can also chat us the questions and we'll read them aloud. So before the speaker gets started, I'm going to hand this to our Associate Director, Ralph. And Ralph, please go ahead.
Yeah, it's my pleasure to introduce Professor Alexandra Anderson-Frey, Assistant Professor, Department of Atmospheric Sciences, University of Washington. She's received her degrees, a couple of institutions in Canada, also spent time postdoc work at Goddard, and ultimately got her PhD in meteorology at Penn State, and also spent time as a postdoc at Sims, which is in Oklahoma, I believe, and started at University of Washington in 2019. And so, yeah, she's going to tell us a lot about tornadoes. So I'm looking forward to her talk. So welcome.
All right, thank you so much for the invite and for the opportunity to geek out a little bit about a topic that is near and dear to my heart. I apologize in advance for the lighting here. It's a rare sunny day in the Pacific Northwest, so I don't know what's going to happen here throughout the day. Yeah, feel free to jump in with questions as we go. I was telling everyone that I've got a fairly flexible talk here, so feel free to jump in. So as the title suggests, I'm going to be talking a little bit about tornadoes in a variety of situations. Up here is actually a tornado that occurred at the UBC campus up in Vancouver. Got another Canadian tornado, July 31st, 1987. I believe this one was on a campus, I think this is UIUC, I want to say. So a lot of variety in tornadic activity here. So just to give you a brief outline of how I'm going to be approaching the topic, we'll start with a general introduction to tornadoes, where they tend to happen, who they tend to happen to, and talk a little bit in terms of dynamics. If it's been a minute since you saw a mesoscale dynamics class, I do want to do a brief overview here. I'll then get into some of the unsupervised learning techniques that my research group uses, in particular self-organizing maps. We'll talk a little bit about clustering, and I'll highlight some work done by my PhD student, Henry Hua, looking at self-organizing maps for regional analysis. And finally, kind of wrap things up talking about, in particular, using this kind of clustering approach for unusual tornadic environments. So this is the question I always ask my 100 level students: where do tornadoes happen? And the answers I tend to get are very frequently Tornado Alley, Oklahoma, Kansas. Occasionally someone will say the Southeast, but I always tell them in the end there's no wrong answer when we're talking about where tornadoes happen in the US. In the last 20 years or so, there's been at least one tornado in every state in the contiguous US. So perhaps a little bit surprising, this is a data set. This is coming from the storm data set, courtesy of Brian Smith, Rich Thompson, and Andy Dean at the Storm Prediction Center. These are 11 years of tornado reports just being plotted. And I tried to kind of make some groupings of different regions that we may think of when we think of tornadoes. And perhaps surprisingly, this kind of grouping of sort of Tornado Alley, Southern Great Plains states only accounts for about a third of all tornadoes in the US during this period, with another third in the southeastern US. And if you kind of squint your eyes, you can see a diagonal line kind of cutting through Mississippi and into the north of Alabama, and it actually trails all the way up. This was from a single event, April 27th, 2011, an extremely severe tornado outbreak with hundreds of tornadoes. If we look at the northern plains and into kind of the Great Lakes and Midwest region, we can see about another quarter of tornadoes occurring there. And if you've been keeping track, you know that we're running out of percentage points here. But in the Northeast, including Maryland, we see quite a lot of activity, all things considered, but only about 3.3% of all tornadoes in the US are in this region. Of course, this is a region of great concern when a tornado does occur because population density is so high. And then out in my neck of the woods, the western third of the US, has about 3.5% of all tornadoes. So we do get activity across all of these states, which often comes as a surprise to the folks living in these areas. But you can see that in particular, we have some activity in the California Central Valley. And there were a handful of papers published in the 1980s looking at these tornado outbreaks, but less research since then. So there's a fair amount of activity going on out in this region. I'm Canadian, so I have to have my requisite Canadian content here. I wanted to highlight this plot. It's a little bit out of date for reasons that I'll be talking about shortly, but this is a plot of tornadoes in Canada from 1980 to 2009. And if you're familiar with Canadian geography, this should come as no surprise. There should be something a little bit suspicious about this plot. Flipping to the next slide here, we see that population density lines up pretty well. I'm going to go back and forth, apologies for the flashing, but you can see it lines up almost exactly. So either tornadoes are actively chasing people down, or much more likely, we are only getting tornado reports in places where there are people to see them. It seems pretty obvious when put that way, but this actually makes a huge gap in our tornado climatology. So as part of this, the Northern Tornadoes Project out of Western University in Ontario and the Canadian Severe Storms Laboratory, which is a new development, are working to fill in a lot of these gaps using satellite imagery, using drone imagery. It becomes quite difficult if you can't detect a tornado directly using radar or storm damage surveys. There's a lot of tornadic activity in Europe as well. The European Severe Weather Database has quite a difficult conundrum on its hands, which is aggregating information from many, many, many different countries that have different reporting requirements and things like this. But we see a lot of activity. Nikolai Dotzek's paper back in 2001 had this really interesting statistic of 1 tornado for every 50 thunderstorms in Northwest Germany, which is quite a high fraction, actually. There's been quite a bit of research on tornadoes in Poland as well. Tornadoes occur in a lot of different regions. You can have tornadoes associated with tropical cyclones. So places like Bangladesh may get the occasional tornado associated with their very frequent tropical cyclone activity. We see tornadoes in certain provinces in China. We see tornadoes in Japan. We see tornadoes in South America, South Africa. Lots of different regions are seeing this activity, but we are hampered by population density, by reporting standards being all over the place from place to place. So as I kind of get into this dynamical discussion, I do want to highlight an important distinction. So this enhanced Fujita scale, this is based on the work of Ted Fujita, originating in I believe 1971 was the original Fujita scale, which has since been updated. This is the way that we assess we approximate the intensity of tornadoes. It's very difficult to measure wind speeds of tornadoes directly, partly because in situ measurements are in danger of being destroyed, and also because remote measurements like radar, since radar paths are tilted with respect to the ground, the further you get from the radar, the higher up you're looking in the storm, which makes it very difficult to get a Doppler radar measurement of a surface process like a tornado without driving the radar directly to the tornado. So instead, we look at the damage left behind and estimate wind speeds based on that. The rating scale goes from an EF0 to an EF5, so from relatively minor damage to absolutely catastrophic damage. And the good news is that these catastrophic damage events are extremely rare. This is good news for everyone, but it does make any sort of research into these rare events upon rare events very difficult. We are, especially if you want to do any sort of data-driven technique, you need to be aware of how rare these really extreme events are. So if over 80% of tornadoes are rated EF0 or EF1, why are we concerned with these really high-end events? Well, if we look at the fraction of each rating scale of deadly tornadoes, so tornadoes resulting in at least one death, about 80% of them are rated EF2 or greater, which is typically the range of enhanced Fujita scale ratings that we call significant. So a significant tornado is one rated EF2 or greater. If we instead look at the total number of deaths due to tornadoes, half of them are coming from this tiny fraction of EF4 and EF5 tornadoes. So I feel like this plot is a good thing to have in the back of your mind as we kind of discuss the dynamics of tornadoes and try to think about what methods can actually provide us with some insights. So talking in terms of dynamics, what sorts of things are forecasters looking for in the near storm environment, and why are they looking for these things? I think that a lot of people with even a passing interest in severe storms meteorology in particular will have some insight into which parameters are important, but may not know the whys and hows of all of it. So a decent starting place is to take a look at environments that are favorable for supercell thunderstorms, which are defined by their rotating updraft. So which conditions produce thunderstorms that rotate in this way? The reason we care about this is that supercells are responsible for virtually all high-end tornadoes, as well as many high-end hail and many, probably not a vast majority of extreme wind and flooding events. So if we are attempting to forecast supercells, we need a source of rotation and we need a source of rising air. So frequently we use convective available potential energy as a good first guess for updraft strength. CAPE can be readily found on a thermodynamic diagram since areas are proportional to energy, and it's just conceptually the integrated buoyancy from the level of free convection up to the equilibrium level. So at all places where a lifted parcel will be less dense than its surroundings. And this gives us a good approximation. It doesn't include things like precipitation loading, but a good approximation of the strength of the updraft, or as it is often used in sort of a thresholding approach, it can be useful to assess the presence of an updraft. But rotation is a little more complicated. For the mesocyclone, the rotating updraft, we do want vertical vorticity. And this vertical vorticity provides us with a source of vertical vorticity that can be useful in getting that rotation down to the ground. So frequently the way we go about this is, rather than assuming some pre-existing vertical vorticity, we instead assume the much more common scenario of horizontal vorticity being present. And if we think about this in terms of wind shear, with higher winds, stronger winds aloft and weaker winds near the surface, We can imagine a pinwheel situation, water wheel situation, where it's fairly clear that in this kind of flow, we are going to see the generation of horizontal vorticity. As this horizontal vorticity interacts with our updraft, we see the tilting of this vorticity into the vertical, in this case with two counter-rotating vortices to either side of the updraft. And to put it numerically, we can think in terms of the vorticity tendency equation here. On the left, we've just got the storm relative tendency of vertical vorticity, and on the right, we have the two terms contributing to this. So we have this tilting process on the right. It's just a cross product between the shear vector and the horizontal gradient of the updraft, essentially. So if our pink circle is an updraft, our updraft gradient, our vectors are all directed toward the center. And knowing the properties of a cross product, anywhere those vectors are parallel or anti-parallel, we have zero vorticity generation via tilting. And anywhere they are perpendicular, we have a maximized or minimized generation of vorticity. So this plot is just another way of showing what we've displayed here. This tilting term is just saying that the presence of an updraft results in two counter-rotating vortices to either side of an updraft. But it's this advection term, the one on the left here, that actually brings us into a situation where we can really say that we have a rotating updraft rather than an updraft surrounded by rotation. And in the case of streamwise vorticity, having gone to Penn State, I have to make a football analogy. Streamwise vorticity is vorticity where the sense of the vorticity vector is pointing in the same direction as, in this case, the storm relative wind. So it's picturing a spiral pass with a football. The football is rotating around the vorticity vector, and that vector is pointing in the same direction as the football itself is being thrown. And in the case of streamwise vorticity, again, following through this equation, on the left here, we have the storm relative velocity. On the right, we have the horizontal gradient in vertical vorticity. This is subsequent to tilting, so we've got our couplet here. And so the direction of the gradient, in this case, is pointing toward the south. And evaluating this dot product, we are going to see maximized vertical vorticity at the center of our updraft. So all of this has been a very long-winded way of saying that the presence of an updraft and the presence of wind shear, specifically with this streamwise direction in the in the storm relative velocity, will give us a situation where we have a rotating updraft. This is necessary but not sufficient information, still quite useful. So we tend to look for relatively high CAPE as a proxy for our updraft strength and relatively high bulk shear as a proxy for the potential for rotation that can be then tilted into the vertical and advected into the updraft. I'm not going to get too into the weeds about the specific processes that lead to tornado genesis at the surface. But there is kind of inherently a problem in what we've been talking about here, which is that we have this horizontal vorticity vector that then is being tilted into the vertical. But because that tilting is being done by an updraft, by definition, we are moving this away from the surface. So how do we get that vertical vorticity down to the surface? And it turns out in recent studies that there are many, many, many different processes that can lead to this final moment of tornado genesis. There's the streamwise vorticity current. There are tiny differences in surface friction that can cause this. It seems to be a matter of which process gets there first. But one kind of straightforward, probably a little overly simplified process that we can think of is the presence of a downdraft that will advect and stretch the vertical vorticity down to the surface. So we can picture a scenario where this downdraft, through conservation of angular momentum, is giving us sufficient vertical vorticity for something to be considered tornadic. So low-level moisture also plays a role because this determines the strength of the downdraft. So in a relatively dry situation where we maybe have very high cloud bases, there is additional evaporative cooling that will occur because it takes much more moisture to reach saturation. And therefore, we see a stronger downdraft on average in a relatively dry air scenario versus a relatively humid scenario. But this is kind of contrary to what we see in the tornado record. We see that in the scenario of relatively dry air, this downdraft actually becomes so strong that it will undercut the updraft. And that mechanism is all of this evaporative cooling and precipitation loading. It's going to bring your downdraft down to the ground. It doesn't just vanish when it hits the ground, it spreads out in a cold pool, which will essentially act as a density current and cut off the important source of near surface moisture and heat from the surface. So instead, what we tend to look for actually is relatively low cloud bases that are sufficient to allow a meaningful downdraft to form, but not so strong that the resulting cold pool will completely undercut the updraft. So when we talk about the parameters that we are interested in for specifically supercell tornadoes, one that I didn't get into in a lot of detail here is low-level storm relative helicity. We can think of this as a proxy for the rotation potential, in particular with the streamwise component. Studies are showing that the lower, the better. If you have a model that can get down to 0 to 250 meters, that may be more useful than calculating 0 to 1 kilometer. And then we often use this LCL height, which you can think of as cloud base height, as a proxy for low-level moisture. And we generally want those heights to be relatively low, corresponding to higher low-level moisture. All right, all of that is maybe a little more of a digression than needed, but I like making sure, especially with a bit of a broader audience, that everyone's on the same page here. And this is one of many formulations of a composite parameter known as the STP, the significant tornado parameter. The version that we're going to be talking about here is actually using all 4 of these parameters and essentially sets thresholds based on climatology, where when we reach all of those thresholds, we have an STP equal to 1, and that becomes an environment in which we are concerned about the potential for specifically significant tornadoes. The STP was designed to distinguish between non-tornadic supercells and supercells resulting in EF2 or greater tornadoes. And here I want to highlight some work from my graduate student, Henry Roy, just demonstrating how unusual the environments in which tornadoes occur really are. His work here essentially took a look at some of these key parameters like CAPE and 0 to 1 kilometer storm relative helicity, and took a look at dates of tornadoes, I believe EF2 or greater tornadoes, and then looked back in the days leading up to that tornadic event to see whether there was a distinct difference. How dramatic was CAPE compared to the day before or the day before that? And what he found was, in this case, these kind of brighter colors, less purple colors, correspond to more distinct environments. So the day before, in terms of both CAPE and storm relative helicity, there is a strong signal there. And there's even a weak signal 2 days beforehand. So it's a little noisy, but the kind of takeaway here is that these tornadic environments really are distinct, and having this environmental data can give us quite a bit of predictive power. So as an example of this significant tornado parameter, I've plotted here values of STP for a particular tornado, the 2013 Moore, Oklahoma EF5 tornado. I do have to specify the date because unfortunately Moore, Oklahoma has been hit by multiple EF5 tornadoes. But for this particular gridded data, which we're going to be seeing a fair amount of here, the asterisk at the center is the location of the tornado. We're just moving 240 kilometers in each direction, northwest, east, south. And what's being plotted is STP. So again, STP greater than 1 is where we start to get concerned about the potential for significant tornadoes. And you can see that we don't really have a bullseye here. We don't have these incredibly favorable environments directly over top of where the tornado is occurring. Instead, it's kind of occurring along this gradient of STP values, which we'll see a little bit more of in a moment here. But why this focus on the near storm environment? I really want to hammer this home. It fairly apparent, but well worth highlighting. Forecasters should have access to this information hours in advance. So having soundings, other observations, or even days in advance via numerical weather prediction. These are broad enough parameters that, unlike something like kilometer scale models or convection allowing models kind of approximating where storms are going to occur, this is much more bulk information. So being able to get information well in advance, even with a relatively sparse observing network, which is really relevant for many countries that are prone to tornadic activity. And of course, when we're talking about these kind of broad strokes parameters like CAPE and shear, pattern recognition becomes extremely important. A lot of what we talk about when we talk about tornadic events kind of boils down to where have we seen this before? What analogs are out there that resemble these atmospheric soundings and these patterns? And the two-dimensional pattern seems to be important as well. With this significant tornado parameter, are we looking at, again, a bullseye of STP, or are we looking at these kind of gradient situations going on? So as a first step for this work, we clustered together similar spatial patterns in the near storm environment. And the idea is that we can then evaluate statistics for each of these clusters. So we're going to be able to extract not individual analogs, but kind of prototypical environments that reflect different regimes in which tornadoes occur. And as sort of a side note from this, we should be able to isolate into their own clusters and then learn from tornadic environments that are really atypical and really unusual in that sense. So one approach, there are many approaches out there that would be appropriate for this particular problem, but one that we found quite interesting and useful was self-organizing maps. And if you're unfamiliar with SOMs, they are an artificial neural network. They're trained using competitive learning, and they date back to the 1980s. So there's a very long history of self-organizing maps, which means there are a lot of tools available to analyze them and a lot of discussion about their strengths and weaknesses. The only user-specified parameter is essentially the number of clusters that you'd like to end up with and what sort of orientation they're in. There's a certain amount of subjectivity involved often in determining how many clusters, how many of these prototypical environments you want to identify. And that comes out because as forecasters are going to be looking at these, you want them to be visually distinct. So not necessarily as much value in a statistically significant difference between two clusters if they're visually identical. But this number can be set more objectively using any sorts of metrics for clustering, things like silhouette coefficient, which measures inter versus intra-cluster variability. Lots of different approaches to set this number, but it's a relatively computationally inexpensive process. So you can do this quite iteratively and run through until you find something that has the visual distinctiveness you're looking for. I'm going to be probably very cavalier with my terminology here and use the word cluster and node interchangeably. So essentially, each of these clusters will begin with a bunch of random noise. So if you say, I want to end up with 9 clusters, it will populate these 9 clusters with random noise. Each of these nodes will then be compared with each map in our data set. So when I say map, I want you to think back to the Moore, Oklahoma STP grid, just gridded values of significant tornado parameter to reflect the environment. The kind of first approach at this used 15,000 or so tornado events. And as these comparisons are made, the nodes are then nudged to more closely resemble the actual data. So there's stronger nudging for more similar nodes, and that's where this concept of competitive learning comes into play. We seek the best matching unit, which one of these comparisons matches the most closely, and then we push it to more closely resemble this. This is ideally a process that through iteration will converge to a solution here. And with enough repetitions, the nodes stabilize into this number n that we gave it, statistically distinct maps around which we can then cluster the data set. And the actual clustering process is typically just done using something like a Euclidean distance metric or something similar. All of this is to say that we start with an input, 15,000 maps of significant tornado parameters surrounding 15,000 tornadoes, and then our output will be a series of clusters. And what this might look like is we'll have a whole stack of maps of STP, and we may wind up with, in this case, a 3x3 grid of tornado environments. So one of the really nice features of self-organizing maps when they're applied to two-dimensional data like this is that they retain the sort of topology of what's going on. They can recognize some patterns, and the output looks like the input. So these maps on the side, all of them have this white dot at the center as the location of the tornado, and then 480 by 480 kilometer grids surrounding each of those tornadoes. The white contours here are being placed at a value of STP equal to 1, because that's sort of the threshold beyond which we get concerned. And you can see that there are a lot of different environments going on here. Oh, these green numbers indicate the number of events sorted into each one of these clusters. So there's no requirement that all of the clusters be equally populated. You can see, taking a look at node 1 here, that we've got this really extreme near storm environment where we have significant tornado parameter values that are very high and that are centered directly on the location of the tornado. So we have this kind of bullseye scenario, but we also see that these are not very common. Only about 103 out of these 15,000 or so events. If we look down at node 7, we see that we actually have a gradient in STP values, with less favorable environments to the west of the tornado and more favorable environments to the east, which looks a lot like something like a dry line or a cold front kind of scenario. And then in direct contrast, we have something going on with node 6 here, where we have these really unfavorable environments, or extremely marginal environments, accounting for about half of the whole data set. So we'll come back to that in a moment, but I first wanted to show you, again, some work of Henry's demonstrating what you can do when you kind of take this self-organizing map approach into a more sophisticated direction. So one of the things that he did here, we're looking specifically at CAPE values for tornadoes across the US, and he was able to use a self-organizing map, nested self-organizing maps, to identify these kind of 6 regions in which tornadoes occurred and had really distinctive CAPE signatures here, which then allowed him to construct these climatologies of CAPE. So the way to read these plots is on the y-axis, we have the seasonal, time of year. On the x-axis, we have the time relative to local sunset. So on the left, we have daytime. On the right, we have nighttime. And then what's actually being plotted, wherever we see red, that indicates that tornadoes that occurred at that time of day in that month were above average, or in blue, below average CAPE for tornadoes in general. So we can see that in this node 1-1 region, kind of along the Gulf Coast and into the Atlantic states there, we can see that there is a lot of variability along the y-axis, so a lot of seasonal variability in CAPE, but very little variability in along the diurnal axis. So very little change between nighttime and daytime in terms of CAPE for tornadoes. So we're able to get a much more nuanced climatology of what's going on in these near storm environments by separating them according to these self-organizing map approaches. And we can do something similar for 0 to 1 kilometer storm relative helicity. The details are less important here than sort of the overall approach, at least for the purposes of this talk. But I really wanted to highlight that this kind of approach of clustering based on self-organizing maps can also have some sort of geographical implications and more detailed climatological implications as well. So going back to that previous example, our 9 nodes that we created on the basis of these 15,000 or so tornado events, for reference, that's about 15 years worth of events. We're then able to very straightforwardly take a look at each of these clusters and get some statistics involved. So we've got probability of detection here, the percentage of all tornadoes with a warning out ahead of time. We've got some different geographical regions kind of broadly defined here. We've got different times of day where this EET here refers to the early evening transition period, 2 hours before until 2 hours after local sunset. And then we've got the different seasons. So you can see that node 1 is in red here. These really extreme environments, very well forecast, which is good to see, and seem to occur pretty even split between the Great Plains and the South. Primarily in the early evening transition period and during the springtime. So these are sort of the prototypical environments that we think of when we think of tornadoes. But this talk is about unusual tornadoes. So we're going to take a look at node 6. Because node 6, we can see, has a probability of detection that's closer to 50% and seems to be much more evenly split across different regions, much more of a daytime kind of scenario with a pretty even split between spring and summer. So this haunted me. This initial paper came out in 2017, and node 6 has been on my mind ever since. So I took a look at some other subsets of data over the years, creating these self-organizing maps and identifying these prototypical near storm environments for things like only deadly tornadoes, only tornadoes that resulted in at least 1 death. And again, the most common environment is the most marginal one. We see that with non-deadly tornadoes as well. If we look at tornadoes that were part of a major outbreak, so EF2 or greater, again, the most significantly populated node is always the one that is the least intense. So the question here is what can we draw from this? What exactly is going on here, apart from hopefully that I've become better at plotting nice figures over the years? Well, the first thing that comes to mind is the representativeness issue here. This is a big concern with proximity sounding climatologies, where we take a single atmospheric sounding to be representative of the environment in which a storm is forming. This is tricky because by definition, thunderstorms and especially tornadic supercells occur in the vicinity of a lot of really tight gradients. So it's very easy to find yourself on the wrong side of the gradient when you're making these measurements. Convective contamination is also a concern. But to try to help mitigate that, we are looking at this full 2-dimensional grid, 480 by 480 square kilometers, to try to capture some of this variability and some of these gradients that we may be slightly off on. So what else could be an issue here? Well, whether or not a tornado forms may be really sensitive to extremely minor fluctuations in the environment. In regions like the southeastern US and to a lesser extent places like Europe, we see environments in which relatively high shear can compensate for really marginal instability. So our significant tornado parameter that is so focused on particular thresholds that have been established in a certain region are maybe going to struggle a little more in these different environments. If CAPE is really limited in an environment, just a small amount of CAPE may be all that's needed to tip the balance. The example of this that I saw a lot growing up in Alberta was that as soon as we hit double-digit dew points, everything popped off. And that's double-digit Celsius, but still not very high dew points were needed for extreme convection to occur. But on the flip side, whether or not a tornado occurs may be completely insensitive to environmental parameters. Once you have a supercell present, it may come down to these really small scale, more stochastic processes. More and more, we're seeing the impact of surface friction. These just might not be the right parameters and might not be at sufficient resolution to really capture what's going on. So to try to explore this, there were so many events within this node 6 that it seemed natural to do a nested self-organizing map and to kind of take this to the next level and consider what all of these subnodes can tell us. Is this truly a situation where there are favorable environments happening, but when they all get averaged into that one cluster, we're just losing that variability? And we do see a little bit of that. Places like Node 1 here and Node 7, we do see environments in which the tornado is not occurring in the immediate vicinity of the favorable environment. But again, with 41% of events, we see that this very marginal Node 3 is still by far the most common node in this data set. So this appears to be a pattern that is persisting, no matter how we look at the data. The next question is, okay, well, is this node just isolating environments in which we have really, really minor tornadoes? Are we looking primarily at EF0 tornadoes? And it turns out that if we look at a lot of these things like the geographical distribution, seasonal distribution that we saw earlier, but also things like storm morphology, is this from a linear system or a supercell? Are we looking at different intensity, different deadly tornado percentage? It turns out that all of these nodes have very similar data. Next, we look to STP and we say, well, significant tornado parameter is a composite parameter. Are there differences in the component pieces? Are we seeing these situations where tornadoes are occurring with relatively low CAPE because we have so much shear that it's overpowering that resistance? I've just plotted these quick box plots for each of the 9 nodes, looking at the 4 component pieces of this formulation of STP. I don't see anything statistically significantly different between these 9 nodes here, looking at CAPE, looking at shear, looking at LCL heights, looking at storm relative helicity. They all look functionally identical. There's nothing really telling about node 3 except that it has more data in it. So where do we go next with this? This is a complicated problem, as it turns out. Well, for one thing, repeating the analysis with other reanalysis data sets is useful. Everything I've shown so far has come from the rapid update cycle or rapid refresh model, because that was commonly in use in the kind of operational setting, but reproducing this with other reanalyses is useful. But I think something also to keep in mind here is that when we have this ingredients-based approach to forecasting, we're considering scenarios in which the presence of all of these ingredients simultaneously gives us this kind of necessary but not sufficient favorable environment for tornadogenesis. But in reality, tornadogenesis may be pretty far removed from when that supercell first gets generated. There may be several hours between those processes. Not all ingredients must be present at the same time for a storm to thrive. So we can gain a lot of insight looking into the temporal evolution of a lot of these parameters as well. That's been one direction of research here. But we also have this great sandbox to play in. Using these nested self-organizing maps, we have these tornado cases that have widespread marginal near storm environments and that are representative of a bunch of different regions, a bunch of different seasons, a bunch of different times of day, and so on, different storm modes. So taking a look at the radar imagery to figure out what exactly is going on about these near storm environments and how they're evolving over time in particular is sort of the next direction to go with a lot of this. So in the last few minutes here, I just wanted to display some interesting work done with various groups on and off campus here, looking at some different approaches for weather forecasting. Kind of encouraging folks to look a little bit beyond the sort of convolutional neural network, UNet architecture, a lot of the approaches that we've been using with the caveat that those approaches work well for many, many things. And it's I think useful to be aware of when to innovate and when not. But there's some promising work going on in using stable diffusion for weather forecasting. There's a paper that just came out a couple of weeks ago where we looked at the Pangu weather deep learning forecasting model, looking at these different kind of storm relevant parameters like CAPE, shear, storm relative helicity, and seeing how well it performed relative to the GFS. In particular, I think what I want to highlight from some of this work is the importance of moving beyond really simple metrics of evaluation and forecast skill, beyond RMSE and actually looking at spatial statistics and parameters that are really relevant to what we're doing. We're at a point now where we can probably move beyond a lot of the 500 hectopascal heights as our metric of skill and move into these more complex parameters, see how things are going there. There's also been a little bit of work looking at generative AI, trying to emphasize the importance of forecaster input for anything that is going out to the public, but trying to reduce the fire hose of data by prioritizing different data streams, getting into the weeds a little bit there, but trying to find useful use cases for generative AI that are not reproducing things that are already done well, that are not just reinventing the wheel and are instead providing support for forecasters rather than trying to replace imperfectly skills that are already there. All right, all of that was a little bit of a digression, but I want to thank you for your time. I'm really happy to answer questions. If not here, feel free to reach out to me on Blue Sky or on email, and I'm always happy to talk about more of this. Thank you so much for your time.
Thank you, Dr. Anderson-Frey. So now we have a couple minutes for questions. So if anyone has any questions, you can go ahead and raise your hand and you should be able to unmute yourself. Otherwise, you can put that question in the chat. Go ahead, Dr. Lee. Oh, wait, you're muted. Let me unmute you.
Can you hear me now?
Yes, we can.
Yes. Hi, Alexandra. Thank you for a very comprehensive review of this important problem. I just wonder, you mentioned that when you show the map of the tornado occurrence, Canada and US, you show the, even make a remark that it's a tornado chase people or the other way around. So I just wonder if tornado have really, human have any footprint to affect tornado both from the surface change surface condition or atmospheric condition. In particularly, I'm working on aerosol. If those air quality stuff could have effect, as we know that air quality does affect severe thunderstorm, especially lightning. So I wonder if tornado could have been affected by this or even by changing surface condition as well.
Yeah, this is a complicated problem, as I'm sure everyone is really aware. The interaction of aerosols and convection is a very complicated one. I think a little bit clearer is the impact of sort of humans on processes like tornadoes via surface land use change. In places like Alberta, Oklahoma, we see a huge injection of moisture into an environment via leaf out as soon as crops are ready. Anyone who has lived in the Midwest knows about the corn sweats. once you have that large injection of moisture via evapotranspiration, that certainly feels like it would be a meaningful source of additional input into these near storm environments that could result in really tornado favorable areas. So, yeah.
Thank you.
Thank you.
Thank you, Paige. You can go ahead and ask your question.
Yeah, thanks. Can you guys hear me okay?
Yeah.
Okay. Sorry, my internet is a little unstable. Thanks for the great talk. Even as an oceanographer, it was pretty easy to follow, which I think is a high compliment for a tornado talk. My question was about the nested clustering. So can you help me understand why you did the nested clustering, which I understand is you clustered everything and then you kind of took the values just for one cluster and clustered them again, when you would choose to do that versus just using more clusters in the initial clustering?
Yeah, that's a really good question, and I did kind of brush over that. I think for this particular problem, we have kind of this node 6, which is 7,500 events or something similar. And just running the original SOM with more clusters, that node remained unchanged. So everything else, it got more granular and tried to split those into more areas, but that node 6 stayed the same. So in order to really pick that apart, pretty much the only approach we found that was useful was to do this kind of node within a SOM within a SOM approach.
Okay. So like the intra cluster variability for that one was like
Right.
much less than the intra cluster variability of the other clusters then.
Yeah,
Okay.
correct.
Okay, cool. Got it. Thanks.
Yeah, thank you.
Do we have any other questions? We have a couple more minutes.
Yeah, this is Toshi. Can I ask a question?
Oh, yeah, go ahead, Toshi.
Okay, I'm kind of hesitant to ask this kind of like strange, maybe a very, very strange question. And I understand that those scale dynamics and then, all sort of environment things. But so in the future, do you think can we suppress artificially by the occurrence of the tornado? This is a bit related to the Junchin's, the question that anyhow, large scale environments given by the, whatever the general circulation, mass scale circulation by the Earth, but microphysics we can still control, somehow, and I don't know how much, but what do you think in the future? Once we figure out forecasting, now we can next is the control. That's what John Simpson used to say it and all the times. So what do you
Right.
think in your perspective? It's a weird question, I know it.
No, yeah, this is, and it's refreshing to talk about this on a level that isn't the guy next to me on the airplane saying, "Why don't we just nuke all tornadoes?" On a more sophisticated level than that, I think that there have been a couple of really interesting papers in the last 2 years or so published by Paul Markowski looking at the volatility of predictability of tornadoes. And I think sort of as a consequence of that, we're moving into this understanding that there are many potential roads to tornado genesis, as long as you have this supercell thunderstorm. And there are so many potential processes that can get us there that I would be at a loss to identify a like mitigation strategy that would actually kind of cut off that process. So thinking of the movie Twisters, and it was kind of centered on all that. There's some kind of double counting of the thermodynamics there, and it doesn't quite work out. But I think as we understand how complex tornado genesis really is, rather than making the process more fragile and more dependent on sort of a single process that we can disrupt in one way or another, it looks like we're finding so many different ways for this to occur that it's kind of a game of whack-a-mole to try to stop this process. So personally not very optimistic about some mitigation strategy in that way.
I see it. Okay, right. Thanks.
Yeah, thank you. That's a fun question.
We probably have time for one more question if anybody has any last minute things off their chest. Okay, well, in that case, let's all say thank you to Dr. Anderson-Frey for this great talk. And thank you for everybody else for coming and supporting this series. Our series will continue on Monday, next Monday. Unless it is a holiday, that's always a little bit confusing to me this time of the year. But anyway, thank you all. Have a wonderful afternoon.